Okay, we're going to get going and diving into module number 9, which is linear motion elements. In module number 9, you're going to notice that in our learning plan, we're going to be looking at chapter 17 in our book. And I do have a PowerPoint here that we're going to be following along with. Additionally, there's not going to be any practice problems. There's only going to be an assignment, okay? And I'll talk about that assignment when we come upon it in the book as we go along. So, you'll get to look forward to that. So a little bit less work here for our assignment number 9. So I'm going to, I should have stayed there. I'm going to go underneath and I'm going to look at our PowerPoint. And as I said, this is going to be chapter 17 in our book, and we're going to be looking at linear motion. So at the very beginning of the chapter here, it talks about what our objectives are going to be. And we're going to be looking at two distinct types, similar but different types of linear motion that's used a lot out in industry. And that's going to be power or lead screws, which they're a lot of times referred to, and then also ball screws. And we'll see how they're similar, but we'll also see how they're different. And then we're going to look at sizing those and kind of comparing them in an application and seeing, you know, some of the cons and the pros of each one of those. So on page 643 at the bottom, you are the designer. This is a section that they always have at the beginning of our chapters. And sometimes we look at these, sometimes we don't. But today we're going to look at it because it's going to specifically apply to the application or the example problems that we're going to be looking at in our chapter. So what I want you to do is I want you to take, I'm going to give you 3 minutes. You're going to, if you would, speed read the You're the Designer section here. And then we're just going to talk about a couple of the elements and then we'll proceed on. So as we get done with that reading, that looking at You're the Designer, not very long, but you're an engineer at a company and you want to look at, I'm going to go to my next slide here. This is an overall view of what you're going to try to do. This is concept wise, right? So we've got a hatch that we need to raise and lower. And it says that we need to raise it, I think it said 15 inches, right? In 12 seconds. And then we have to lower it 15 inches in about 12 seconds as well. And right now they've devised a plan concept-wise to look at using what we call lead or power screws, okay, that are going to take this hatch. It's attached right here, okay? This red part is attached to the hatch, and it's going to basically just raise it up and then lower it back down, and then raise it up and lower it back down. So it's not like on a hinge or anything like that. It's just going to go up and down, up and down. And you'll notice that what they have, these are the lead screws that are threaded. And then there are these, they call them nuts, okay, that are on there. And then they're calling this part the movable yoke. And that's really what's going to keep them kind of in tandem at the same level. And it's going to, then you're going to have two, if you would, columns of these Acme screws that are going to go up and down. Now, the nature of the Acme screw is that we are going to rotate them. And that is going to then have that, that nut travel up or down depending on the direction of rotation. Okay. So, so you'll notice that they're tied together with a chain, and then that way they're going to be, you know, going at the same rotational speed up and down. Okay. So what you need to do, as you know, well, I should ask you, what are you tasked with doing? Like, once we kind of know what we're going to do here, what are we going to be focusing on, and what are the elements that we need to consider as we're putting this together? And I'll look at the chat as well, if you guys want to put anything in the chat. So what are we tasked with doing here? Like, what is the main element that we're going to be concerned with in this chapter? Yeah, the lead screws here. They're calling them power screws most often, but they're also referred to as lead screws. That's the terminology I've always used. So these two lead screws right here, okay? We need to devise like how large they need to be, and then also how much thread engagement do we need in order to lift this, okay? Other considerations that we need to think about when we're looking at these lead screws as they talked about in that section. What the pitch is, what the rotational speed needs to be of those, of the lead screw itself, so that we can accomplish that travel of 15 inches in 12 seconds, right? One way and then the other. Good. Yep, the size, the pitch. What else? Torque. Yeah, what is the torque that we're going to need in order to, and we use torque because that's rotational work, right? So instead of pushing something a distance, it's rotating something. And then in this case, we're going to be lifting or lowering that particular item. Good. Anything else? What was that? Go ahead. Go ahead. Yeah, the hardness level of the screws or the material that it's going to be made of. Absolutely. The type of thread. There are two different types that we're going to be talking about. And I know it's a little bit early in the chapter, but we could consider either a lead screw, as we're going to see it, where it's just really like a literal screw kind of going up and down, or a ball screw where it utilizes balls that are in there that that mimic ball bearings. Okay, so there's some advantages to that as well. So really kind of looking at what is going to be, better for this particular application. Anything else that you can think of that needs to be considered here? Now, there are other ways to accomplish linear motion. There's a lot of different ways to accomplish linear motion, but this chapter really just focuses on these screw type of linear motion, taking rotational motion and switching it over or converting it into linear motion. Okay. So we're going to come back to this because the two examples or the three examples that we're going to be looking at refer back to this exact design. Okay. So, we'll kind of keep that in our back pocket. So getting into the chapter here, looking at power or lead screws. So the basic function of a lead screw is to convert rotational motion to a linear motion. Now it says here of a lathe spindle. That's a very common place where lead screws are used because a lathe, as you know, runs horizontally in and out with its travel. Okay. And a lead screw is actually going to be what that lathe is going to run on. Now, when we look specifically at power or lead screws, they are, and I like this picture here on the right-hand side in the upper right-hand corner. This is going to be the actual threaded rod, okay? And there's a couple different types of threads that we can use that make sense for these applications. But what I like about it is when we pull these two blocks apart, you can see that the inners is just the thread that matches the lead screw itself. Okay, so that would be like the internal thread, right? Like the tapped hole, if you would be what this outside like brass is. It's probably made out of brass type of a block. And then it just is going to ride on the threads of the rod itself. Okay, so, and they can come in not only blocks, but that's what the inside of this nut looks like on either one of these two. Okay, so it's a really quite simple design. Okay, very simple design. Let's take a peek at this YouTube video, which shows us a little bit of motion. There's really no sound here. It's just looking at, as we rotate that rod, this nut is going to then have the ability to go back and forth. And so we would mount something on here. In this case, we are going to be orientating it vertically for those two sides. And then we would mount, in our case, what they're calling a yoke to then, go up and then down and then up and then down. And then just by reversing the direction of rotation, we'll then reverse the direction of the lift. Okay. Now, as I said earlier, there's a couple different types of thread forms that are popular for lead screws. And the three are going to be the square, the acme, and what they call the buttress. Now, the buttress is the one that has it's the one in the middle up on here on this illustration. They didn't have a nice little pictorial of that particular one, so I wanted to show you this illustration, which I thought was nice. Now, really the difference between them is the thread form. Now, the square and the buttress are the two that are actually most efficient in terms of like getting the job done. But the acme is more popular because it's easier to create and machine. Okay, so many times you're going to see these lead screws made with acme threads. Okay, and they're just bigger, chunkier threads, much of the same terminology that you are familiar with in working with fasteners. We're gonna, is really here as well. It's here too. Keep going. Another example of a place that we can use these linear motion type of lead screws is going to be in the form of a jack, as we see here. In this case, we've got a worm gear that rotates this collar around here, and then you can see that the lead screw is in the inside, and that's going to control the height of the platform or the jack going up and then reversing this and then going back down. Okay, so another really good application as we see here. Now, lead screws are used when we have pretty high forces that we want to move. So things like machine tools, they're very popular there. In something like a jack situation when you're trying to lift something that's, pretty heavy and you want to gain a mechanical advantage. So, so the lead screw helps us with that. Other things that are going to accomplish linear motion are things like, hydraulic and pneumatic cylinders, but sometimes they can't pack the punch, if you would, or hold a load when it stops like a lead screw can. Okay. So sizing a lead screw. So when we're performing, there's going to be some stresses that are going to occur. And the two types of stresses that we have are going to be tensile stress area that we want to be concerned about. And it's really tensile and compressive, but usually tension is where it's going to be the limiting. And then we have direct shear across the threads themselves. So if we look at the following equations in our book, we are going to see the variables. So equation 17.1 looks at the area in tension. So I'm going to go underneath my camera here. And on page 644 at the bottom of the second column, you're going to see the area in tension, So as we look at this, and I'm actually going to peek back up here really quickly. Now we have a rod, and what's happening is these are engaged with that nut that's attached to the yoke. So if we're going up and down, you can imagine that we are axially down the axis here. We are going to be either pulling or pushing down on each one of those rods. That's going to be the tensile and the compressive stress that we end up seeing. So as we look at the diameter of our rod, we can determine what the appropriate amount of area is across that diameter. So from strength of materials, you guys would have talked about probably relatively early on in strength of materials about axial stress. Okay, and axial stress, and I know the equation isn't in here, but axial stress was this symbol sigma, right, is equal to, and depending on the book, it would be force divided by area. Okay, sometimes it would be P divided by A. Okay, and as we look at this, so for instance, when we do this, we would have seen this on the tensile test. We would take a specimen, and here's its center. Okay, and we would have a diameter, of some sort, and then we would pull it apart, right? So if it's on that tensile test, we would pull it, and then we would let it go, and we would see how far it would deform. But we were always calculating this stress, and that's an axial stress. The area is the area of the circular portion in here, or the cross-sectional area as we're going along, or perpendicular, if you would, to the force that we're using to pull that apart. okay? So the area in tension that they're referring to here is going to be this area as we would pull or push this, and we want to know how much area do we need. Now, what they do for the area is they use an average of the pitch to the outside diameter. So when we look at, no, they don't have great illustration here, but when we look at an Acme thread, and I'm just kind of going like this, they're going to take an average kind of between here and what would be the root diameter. So they're going kind of in this area right here. What would that diameter be on the other side of that thread as well? Does that make sense? That's the diameter that they're taking when they're looking at this one. So not at the very tippy top, not at the pitch, just in between the pitch and the root diameter of that thread. Okay. So if we look at the charts over here, if we look at the charts on the following pages here, which actually they are also on page 645. I'm going to zoom in here so we can see the columns. You'll notice that this is a chart for the preferred Acme thread, screw threads. And on the left-hand side, this is going to be the nominal major diameter. Major diameter is always going to be the largest diameter to the outer portion of that tooth. Okay. Then it's telling us how many threads per inch there's going to be, and that's lowercase n. So if I measure for an inch and I count how many threads there are, for the first one here, that's going to be 16 threads. So that's a 1/4 inch diameter. It's pretty darn small. So it's a pretty fine thread that we're looking at. Okay. And as we get larger, you're going to notice 1 3/8, that's a pretty large diameter. There's going to be only 4 threads if I would take a linear inch along that length. Okay. Now pitch is going to be the same thing that it was for threads. And pitch is going to be basically measuring. Most often we measure from the highest point on one thread to the same highest point on the next thread. And it's a physical distance between those. So the pitch is going to be 1 over however many threads there are. And that gives us how close or how far those threads are apart. Okay. The next one here is going to be the minor diameter, or a lot of times referred to as the root diameter. That's why it's DR. And that would be the bottom of the actual thread. Here's the minimum pitch diameter. And then these last 2 rows are the ones that we're interested in when we start talking about stress. So the first column is going to be the tensile stress area. So that's when I'm pulling it along its axis and I'm pulling it apart. And this is going to be the tensile stress area that's going to be like effective. That's going to be what's going to be holding this together. Okay. And on the right, the very last column is going to be the shear stress area. This is going to be the shear that is going to occur vertically in our case across the actual thread. So like shearing off the threads, like they're going to actually, come off. There's a certain amount of stress that those can take. So that's the area in shear that these particular sizes can accomplish. So as we go down the chart, you're going to notice that the area gets larger because our diameters get larger. The rod physically gets larger. Okay. So we'll be coming back to this when you look at sizing, what would be the appropriate lead screw to use. Oops, I want to go there. Sorry. And then this is just a continuation of that same chart to the bottom. Now, as we look here, this is looking at the torque, okay? So the torque required to move a load needs to be known when we are lifting it up and pushing it down, okay? Lifting it up and pushing it down. So the torque that we're gonna look at first is gonna be the torque going up, okay? So this is gonna be like that vertical going up. There are a couple equations here. So we look on page 647. 647, equation 17.2. You're going to notice they have this equation right here for the torque going up. Now, the variables that you see here, zoom in, the variables that you see here are going to be capital F is the force that we need to move, okay? Or the load. In our case, the entire hatch is 25,000 pounds, but because we're gonna be dividing it in two, one of those lead screws is gonna see 12,500 pounds. That would be the force that we're trying to move. D sub P is gonna be the pitch diameter of the lead screw that you chose. Capital L is called the lead. Lead is going to be how far this lead screw is gonna move in one revolution. Okay, and the equation for lead, it's kind of buried in, hold on. What's that? Capital L.
Isn't it just 17.8?
No,
On the bottom of 645.
on 645. I knew it was, oh, there it is. I knew it was like, it's like buried. It's right there. So the lead is going to be basically the pitch. So if you take one revolution, how far is that actually going to go? Okay. And that's what the lead is. And so you'll get a chance to kind of play with these. So that's the lead. That's capital L. Go back over here. It's going to be equal to pi times, and then this is F. That F, that cursive F, is the coefficient of friction. So when we have two materials that are going to be moving relative to one another, like we have for a lead screw, we have to know what that coefficient of friction is. So you can have different materials for those nuts that are going to ride on your lead screw itself, on the rod. And then the rod can be a different material. They don't have to be the same. Okay. So you do need to know what the coefficient of friction is, cursive F here, is going to be, and you'll usually either be given it to you in a problem or by the vendor themselves. Okay. Then divided by, you've got a pi on the bottom again. dP is going to be our pitch diameter. We've got the coefficient of friction again, and then the lead. Okay. Now, this is based on the pitch of our lead screw. Okay, this is based on the pitch of our lead screw. There's another equation where we actually can find it based on the lead angle, and that's down here for the up. It's going to be 17.8. Okay, 17.8. So depending on the information that you have on your lead screw, if you know what the pitch is, you want to use this top one. If you know what the lead angle is, you can use this one as well. Okay, so both of them will give you the same answer, if you would, just different variables depending on what you know. Then the other torque that we have is going to be the torque when it goes down the lead screw, and it's a little bit different. And you'll notice here that now we're going to be subtracting off the lead rather than adding it, okay, on the top and then adding on the bottom. So it's just a little bit different. It's just the difference in the direction that you're going. But same variables here when we have the pitch. And then over on the right-hand side, you're going to see the same equation, but it's not the same equation, but it's based on the variables for the lead angle as opposed to the pitch, okay? The lead angle equation is going to be 17.3. That was the one that you were looking at, BJ, and that's going to be right here. And again, we can calculate that lead angle knowing the pitch, but again, depending on, what you have available and what you prefer to do, there's two ways that you can calculate both of those torques. Now, the first equations that we have there were the square threads. And again, they're the more efficient thread, and they're used a lot, but the Acme threads are also going to be used quite a bit too, and mostly because of their ease of manufacture. So this equation for the up and the down changed slightly just because the thread form is different, and there's a thread angle of 14.5 that has to be added into that equation. We'll see in just a bit because of kind of that V that's forms on our Acme thread, as opposed to it being sides that are straight up and down because the other ones were square. So if I go back over here and I turn my page, you're going to notice that we have two more equations at the top, but these are specific to Acme threads. On the right-hand side here, they compare the two thread forms so that you can see the difference. And this one has the 14.5 in there because of those angled sides, okay? The examples you're going to be doing are going to be Acme threads. And then efficiency. Efficiency is going to compare what you put in to what you get out, okay? So the ratio of the torque that's required to move the load without friction, and then also with the friction. The friction is going to be where we see the most losses. Now, when we have lead or power screws, because of the fact that there's a lot of surface contact between the inside of that nut thread of the threads of the internal threads and the external threads on the actual lead screw itself, we're going to find that the efficiencies aren't so great for lead and power screws. They're going to be anywhere between like 20–30% efficient is about all that you get out of them. But you can also add lubrication and play around with different materials to improve that, okay? Now, efficiency may not always be a concern, especially if you're looking at applications where you have lower RPMs and maybe you're lifting things that are pretty heavy. So, and then costs. These are going to be less expensive than what we're going to be talking about next, which are ball screws. Okay. So the efficiency equation is going to be in the middle of page 647. And it's this lowercase e right here. And there's two different versions of it, just expanding out the torque. So the torque with the little prime next to it is without friction. And then the torque with the U is going to be the torque with the friction. Okay. And then very lastly is calculating the power that's required for these applications. So what is the horsepower? Knowing the torque and the rotational speed. And it's our familiar P is equal to T times N divided by 63,000. Now, remember that for this equation, torque is going to be in pound inches and our N is going to be in RPMs. The cancellation of the units is right here in the 63,000. Okay. So, and then P is going to be in horsepower. So there won't be cancellation of units here. The 63,000 does it for us, but in and out of the equation, those are the units for each one of those variables. So torque is pound inches, rotational speed N is RPMs, and horsepower, power is in horsepower. Okay. And the 63,000 is the cancellation of the units. Okay. Here's the good stuff. So now let's take a look at example problems 17.1 and 17.2. This is your assignment. Okay, this is your assignment, and you really only have two problems that you're going to do. And this is the first problem that's going to be assigned. Your assignment number 9 is to create an Excel spreadsheet to complete the design calculations found in these two example problems. One file for both of them, because 1 and 2 are like a continuation of the same problem. Okay, so let's read the problem statement, but then you get to, after we kind of get done with this chapter, kind of going over things, then you're going to go through and write the Excel spreadsheet for this. Okay, so going underneath here, what's nice about this book is the examples are always nicely laid out, and then you have the answers as you go. So it says there are 2 Acme threaded power screws that are to be used to raise a heavy access hatch as sketched in figure 17.4. That was the "you are the designer" that we looked at, okay? The total weight of the hatch is 25,000, divided equally between the 2 screws. So each one of those screws is going to see half of that, okay? Select a satisfactory screw from table 17.1 on the basis of tensile strength, limiting the tensile strength to 10,000 PSI, okay? Then determine the required thickness of the yoke that acts on the nut of the screw to limit the shear stress of the threads to 5,000 PSI. For the screw thus designed, compute also the lead angle, the torque required to raise the load, the efficiency, and the torque required to lower the load. Use a coefficient of friction of 0.15. Okay? So that's what I'm going to task you with, because I want you guys to then, as you look at this problem, you're going to see, it's going to show you exactly what they did in each one of those places. They're going to give you the equations, the units, and what you want to do is write the spreadsheet that is going to go through this problem. Okay. Now, as a continuation of this very same problem, example 2, it says it is desired to raise the hatch a total of 15 inches in no more than 12 seconds. Compute the rotational speed of the screw and the power required. So they again go through that process here as well. Okay. And that's as far as I'm going to take it, because this is something that when you get out in industry, you're going to kind of have to use probably vendor catalogs that are going to walk you through these processes, but you're going to kind of have to pick at it a little bit. And then having you do the Excel spreadsheet just helps you to, I don't know, kind of pick those apart, critically think, make sure that things are lined up. When you do the Excel spreadsheets for this file, so again, one file, for example, 1 and 2 together, you can do it all in one spreadsheet. My expectation is that you're doing some professional looking spreadsheets, meaning I don't just want the equations in the cells, put some borders, put some color to it, you know, kind of make it super nice. You don't have to make it like, I don't know, it doesn't have to be crazy over the top. Perfect. But I want you to at least make it look nice so it's easy to read and to see where the results are. Okay. You can mimic the type that we've been using throughout this class, like the blue is the input, the green is the output, or whatever you want to do. Make it your own, but go through this process. So that's your assignment. Okay. And then we're going to move on. Okay. Ball screws. Ball screws is the last part of this particular chapter. And ball screws have a basic action similar and really the same as a lead screw, except the way they accomplish this is by adding these reciprocal or reciprocating balls on the inside. So what this offers us is less friction. Okay. So let's look at kind of what these look like animation wise.
We're all mechanics. DIY.
So here you can see the kind of that inner portion where those ball bearings are. They're running along the grooves and reciprocating or recirculating in there. And as you can see, the form of the thread is also different. The form of the thread is going to be a little bit more cupped, and it's going to then, you know, receive the diameter of the ball bearings that are going through there. So as we look at this and, you know, just kind of thinking, what do you feel might be some of the advantages of an, you know, an arrangement like this? Anyone? Yeah, super smooth. Okay. And why would you think that's going to be super smooth? Yeah, it is a ball bearing, but what's the advantage of a ball bearing? How is a ball bearing different than, you know, like a sleeve bearing or a bushing? What is there minimized? Friction is minimized because lot less contact, right? You've got like almost like point contact instead of like these surfaces that are rubbing against each other, right? So yeah, we reduce the friction a lot because of the ball bearings that are being used in there. Yeah, but it does, as you can imagine, it's a more complex type of a mechanism, right? What do you think is going to be different in terms of economics? You think it's going to be cheaper or more expensive to have a ball screw? Probably more expensive. What about accuracy? Do you think these are more accurate? Yeah, they usually are. Yep. Over time, they're going to wear less. Yep. Yeah. So yeah, so I wanted to show you that. So it's kind of a neat version of this. So we are going to look at ball screws. Okay. So the main difference is that we have those circulating balls in there. So this is kind of giving you a look at each one. And if you look closely on the left, you can kind of see that cupping. So even if you can't see the inner part of your nut here that's going to be going back and forth traveling, sometimes they can look pretty similar. But if you look at the thread itself, those ball screws are going to, they're going to have that cupping effect to receive the diameter of the balls that are on the inside. Okay. So the anatomy of a ball screw. So you're going to have those steel balls that are in there. You're going to have a steel shaft. The ball nut is where you can mount something to that's going to be, you're going to be controlling that linear motion with. There are going to be seals on the ends. These are going to be lubricated internally, and we don't want contaminants getting in and out, of that. And then the recirculating part there, that's going to kind of help the balls kind of travel through in there. And then notice here as well, you can see a nice view of that cupping that occurs where that ball is going to sit and then be able to travel around. Okay. So applications for ball screws are going to be, again, they can be used interchangeably with the lead screws or the power screws, but automotive steering systems, machine tool tables, linear actuators, jacking and positioning mechanisms. So I tried to kind of, help us see a couple of these applications here. This is kind of a schematic of a lathe. So on the top here is the spindle of a lathe, the workpiece, the tailstock, and then underneath to like pull and push the, the entire, like, what do you call that? The bed of our lathe is going to go back and forth on a lead screw. Okay. And they're usually going to be ball screws. Now, Ryan happens to be an expert on lead screws and ball screws, aren't you? Or you used them a lot. You used them a lot in application.
But just put all drive on them. So a lot of the things you cover, they're higher accuracy, higher cost, but less friction, so less heat. Get more speed out of them too. So some of these machines are moving heavy loads back and forth, up to like 15 meters a minute or something. So they can go pretty fast. So as the technology's got better on screws, the ball screws, you'll see machine tools can start moving at a faster rate, so they can cut metal at a faster rate.
Virtually, were you guys able to hear what Ryan said?
Not too bad.
No. Okay, Jacob. So remind me, where did you work? What was the name of the company, Ryan? Unisig. They made machine tools, and they use a lot of ball screws because of the speeds that they would have to move like large loads for machine tools. And they offered, that speed, the less friction, but then also the ability to dissipate heat, which was a big deal, right?
So you get
More speed. Yeah.
make sheet faster, so you can cut metal quicker. So the time to use the part becomes less and less, the more efficient your machine gets.
Right. So the faster you could go using ball screws, which was the preferred method, then would increase your, capacity, your production on a machine tool, whether that was probably traversing in between before you were cutting and then in the cutting speeds as well. Yeah. Yeah. Cool. Yeah. So that's a really great. Now, where is that company in Milwaukee, right?
Yeah, there is. Down balls.
Unisig.
Yep.
Unisig. Okay, cool. All right, and then here you're going to notice this is an application of a ball screw on a high-speed linear actuator. So on the inside, and really this is a linear actuator is going to be like a a piston. What am I thinking of? A cylinder, just an air cylinder or a pneumatic cylinder, but it's assisted here with a power screw or a ball screw. So that can increase the speed, but then also the ability to move loads with higher forces.
Yeah, there is a lot of different linear motion, right? You can use cylinders.
You can,
or,
yep.
Yeah, so cylinders versus a screw. With a screw, you can actually position it and you can keep track of that position as well. So if you want to move a quarter of an inch or an eighth of an inch or 1/1000, you can do that with a ball screw. With a hydraulic cylinder, it's more or less, it's going to go through it and stop, go back. So
Right. Right.
That positioning accuracy as well.
Yeah, great point. So Ryan just brought up the fact that with screws, you get positioning accuracy, and it doesn't have to be the same increment. Doesn't have to be all the way one way or all the way the other. You can increment it at, 1/4 inch, then an inch or whatever, and it's very repeatable and accurate.
Compared to silk.
Compared to cylinders and, yeah, hydraulic or pneumatic. So parameters when selecting ball screws. So axial load is to be exerted by the screw during that rotation. So this is going to be our 12,500. Like, we need to have this amount of load that we are going to be moving. What is the rotational speed of that screw? Maximum static load on that screw. So when it's not moving, how much can it take? Direction of the load, the manner to support the ends. So you'll notice here that there are supports on either end, and this can be either horizontally or vertically. Okay. The length of the screw, the expected life, the environmental conditions, that's all going to play into the type of screw that you get, whether it is a lead or a ball screw, but then also the materials that they're made out of. If we're in a food grade type of application, you're probably dealing with all stainless steel parts. But if you're in, another application where there isn't as much corrosion, or you don't have to worry about that, then maybe steel or aluminum or whatever will be totally fine. So it's endless, and it just depends on the atmosphere. The ball screw load to life relationship. So when transmitting a load, a ball screw experiences the same stresses as a ball bearing would. So when we looked at ball bearings earlier in this class, we talked about an L10 life, right? And that was where 90% of the bearings would achieve 1,000,000 cycles at whatever that load was, okay? And that is very similar. They rate these very much the same way, but many times you're going to see it as a B10 life, okay? And a B10 life just means that it's a ball screw. They're using it in those terms. And they also, instead of revolutions, they look at the distance traveled by that nut, okay? So like 1,000,000. Now I'm second guessing. I forget, it was 1,000,000 inches or linear. Dang it. Now I'm mad at myself. 1,000,000 inches, 1,000,000 inches, 1,000,000 inches, rated travel life. Okay. And I wasn't sure if it was inches or if it was feet. Inches seems like not that far to me for some reason. 1,000,000 inches doesn't seem that far, but I don't know. Maybe you can speak to that, Ryan. 1,000,000 inches. You would look more at the revolutions. Okay. All right. And again, that would go back to the L10 life. So again, very similar to ball bearings. As we look at equation 1712, you're going to notice that it looks familiar to that L10 life calculation that we looked at for ball bearings. Now, the ones in this case are going to be the ratings that we get out of, if you would, the vendor catalog. So our L1 would be our life to our load 1. Okay. So for instance, if we have, 1,000,000 cycles and it's rated, its load rating is 1,000 pounds. Okay. If we, for instance, on our 2s are going to be our actual application. So if we're only going to be putting on, for instance, 400 pounds as opposed to 1,000, we're going to get a longer life out of that. And so we can calculate then the L2 to be the life that we would actually get. You can also put more load on it. So if this is 1,000 that's rated at 1,000,000, and you want to go to maybe 1,200 or 1,500 on it, that doesn't mean that you can't, but you're going to sacrifice life out of it. Okay. And depending on the application, it may be something that you want to do, or you may not want to do it. And that's why you do the calculation. So, so the very same setup as we did for our bearings. The next one is going to be torque and efficiency. So the efficiencies out of a ball screw, as you can see here, are about 90%. That's a big deal. Okay. So, so as opposed to, and compared to those lead screws being between 20, 30% at the most. Okay. So you don't need as much torque to exert on a given load. So in the problem that you're going to do, which is going to be the second example, or actually the third example in the book, is you're going to actually size and look at a ball screw application for that very same one that you're using the lead screw for. And you're going to notice there is a difference in the torque that's required as well as the efficiencies that are achieved. Those equations are going to be on page 651, and they're at the top of the page there. So if I go underneath page 651, the efficiency is right here. Here's going to be the torque to drive the ball screw. And then you're going to have the torque for the back driver, like it's the down, like we did on the lead screw. So the up and the down, if you would. And then I'm just going to peek ahead here for a second. Yeah. Okay. Just wanted to be sure it was coming. So then the next things that we want to consider as we're using power screws and ball screws is critical speed. Okay. In our application, the speeds that we're using aren't very high at all, but there is a chance that when you are going, you know, at higher speeds, that you could get some vibration and some harmonic, if you would, motion going on that you have to be aware of. So there is a calculator there, or there's an equation there for critical speed, and it all depends on how things are mounted on either side, how they're kept in place. And they suggest that you want to be about 80% of what that, at maximum of what that critical speed is, because you don't want to approach having issues as you're rotating this and going fast. The application, like I said, as we're looking at it, isn't a fast speed application, so they don't do it as part of the calculations, but it's good to be aware of that. And that's equation 1715 on the following page. And then, oh, go ahead.
Length is critical with that application and that equation too, if you look at the equation of length square. So it's just, once you start getting longer screws, that's where you have to reduce your speed so you don't get that critical, that vibration.
Ryan just pointed out, you know, based on his experience, he said the length for those lead screws is really important. So when you start dealing with very high speeds, notice that that length is squared down here. Okay. And so it's going to have a major role in, you know, the length of those. So the longer they go, you want to really watch the speed. Do they ever, well, you probably wouldn't. I was going to say you need that whole travel. I was going to say maybe they support them a little bit in the middle. I don't know if there's a way to do that for those. Probably not.
Yeah.
You just have to get larger probably, huh? Keep
Yeah,
getting
those get
bigger.
larger.
Mm-hmm.
What you go to next is rack drive, so rack pinion.
Oh, a rack and pinion.
Yeah.
Okay.
You have a really long travel,
Mm-hmm.
you go past ball screw ranges, you mount the rack to the bed of a machine, and then you'll have a servo motor with a gear on it, so then the little gear spins you back and forth.
Gotcha. So what Ryan shared for those who are virtual, is that there's going to be a point where these become, you know, too small, or you can't get long enough travels out of them. And then an alternative then would be to go to a rack and pinion type of a drive. Good. Good. This is like your stuff, like your subject. That's cool. All right. And then lastly, something to consider as well, and again, in the application that we have, it's just not critical, is when we start looking at the possibility of buckling. In strength of materials, you guys would have looked at columns, and when they start to get longer and you start to put you know, forces down on those, what you can have in compression is that buckling effect. And so you have to know, you know, where is that of a concern? And that really has to do with your end conditions and how they're being attached, whether they are or aren't, and then if there's any supports as well. So so calculating for buckling is going to be another issue that may come up. And again, they have that at the very end, not included in the calculations that you do for the problems, but it's just referring to that that's something that you have to be aware of as well. And then lastly, the materials of the screw. So ball screw, the little balls are going to be made out of very high, you know, very high strength types of materials. So carbons, alloy steels for that rolling technology, and you know, a plethora of things. They can be made, they can be ceramic, they can be, you know, all sorts of things. You know, if you have money to put at it, any material can actually be could be put in there if you would. The power screws themselves, a lot of times are made out of carbon and alloy steels and usually hardened as well on the surfaces for wear. And then the power nuts themselves can be made out of steel for moderate loads, but then, you know, really anything as well. If you're going to notice online, if you do a little bit of a search, there are different types of plastics that they use, nylons, all sorts of things that can be used as well. And then also being aware of lubrications that would need to be in there for maintenance. So our last example is going to be example 17.3. And what you want to do is here too, you're going to create a second spreadsheet, but this one is going to be for sizing a ball screw. And in this case, you're going to be looking back at that original application, and you will be going through the same process and then doing some of the comparisons with torque and efficiencies to see how it compares to the lead screw. Okay. So for this chapter, it's a little bit different. I'm not assigning any problems out of the back of the book, and we don't have any practice problems to do. What I want you to do is kind of now get an overview of the chapter, kind of get your nose in there, and then you're going to develop the spreadsheet to do the problems that are there. Okay. And then you have the answers and the process to assist you. Any questions? All right. So before I kind of leave this, let's just take a peek at assignment number 9. Says we're going to create an Excel spreadsheet to complete the design of a power screw application as presented in problems or example problems 17.1 and 17.2. I'm giving you 10 points for each of those, so 20 points total for that one spreadsheet, and then a second spreadsheet for the ball screw application. Okay, and that one's going to be worth 10 because it's a lot shorter. Okay, again, reminding you when you do your Excel spreadsheet, make it a nice little form, use borders, colors, bolding, whatever it might be so that it's easy to use. Add instructions if you feel like they're necessary. Don't forget units and variable names and such. So kind of like the stuff that we've been practicing. Are there any questions at the moment? All right. Okay, so then that's module number 9. I'm going to stop recording.